Okay, so we talked previously about the process concept and the mechanism that the operating system has for creating processes, forking them, executing them, killing them, and so on. Once we have the ability or the mechanism to create processes, we have a bit of a problem. And that problem is the operating system needs to decide which process runs at any given time. And this is one of the most fundamental algorithms or policies or techniques that any operating system needs to support. And we call it process scheduling. If you remember from before, we have a process state model. A process can be in the ready state, meaning that it's ready to be run. That means it's also schedulable by the operating system. We have the running state, and only one process is in the running state at any given time for a single CPU system. And that means it's running and using the hardware and the memory management hardware and the CPU and the algorithm, the arithmetic logic unit, and all the things that are in the CPU. And then there's the block state, meaning that the process exists, but it's not really ready to run because it's waiting for something, typically waiting for an IO. Of course, a process needs to come into the world from someplace. Typically a new process will come in as ready. And then typically a process will terminates usually while it's running. It can terminate while it's both ready and blocked as well, because a process might be terminated really at any time. But typically a process finishes in a healthy state, finishes running, and leaves from the running state into some sort of a terminated state. But the question is, if there are many processes that are ready, which one should run next? That's the process scheduling model. That's the process scheduling problem. Which of the many ready processes should run next? And the key thing here is we're separating the policy from the mechanism. The mechanism is we can create processes and we can schedule them. The policy tells us which process should we schedule. It's the algorithm. It's which process is scheduled at which time. And by separating these two, we can actually have many different algorithms for scheduling processes, or we can have many configurations of a single algorithm for scheduling processes, all using the same process creation and context switch mechanisms. So our mechanisms are processes, specifically the creation and termination of processes, and then the switching of processes. Stop one process by saving its state out to memory, and then establish a new process by reading its state into the CPU, overriding the CPU, the register contents, and therefore you have the ability to switch processes. And then the policy then is process scheduling. Which process should run next? Separating the policy from the mechanism this way allows us to make the mechanism solid, very, very solid, while changing the policies as we go along through the years, as we learn more, and as we get better and better with better algorithms for scheduling. So we also talked about objectives. And one of the main objectives for process scheduling is to have good performance. And there's various criteria that we can use for evaluating whether a process scheduling algorithm has met our goals or met our objectives. One is CPU utilization. That is, how busy is our CPU? That's one measurement or criteria that we can use for a process scheduling algorithm. How busy does it keep the CPU? There's throughput. That is, how many processes or how many jobs. A job is what we can call a process that goes from beginning to the end. It's healthily does its job, finishes, and then goes on. And then we can go on and schedule other jobs and have them work and so on. How many jobs have finished in a given unit of time? That's the measurement of throughput for the system. Turnaround time is the amount of time it takes for a process to go from start to finish. That is, when the job is submitted, that's the beginning of the process, to job termination, that's the end. How long does that take? What's the average turnaround time for the processes in our system? And there's response time. Response time is a measurement of how long does it take from submission to actually get a single response back from the process. So in other words, if the process may finish quickly, but if it actually waited for a while before running very quickly, then the initial response back to the user might have taken a long time. We try not to do that. We try to have a low response time. We try to have all processes respond to their users frequently and quickly so that the users maintain that illusion that an operating system is running many, many processes all at the same time. And then finally, for real-time operating systems, we might have other criteria such as have we made our deadlines or have we missed the deadlines? That really gets into real-time operating systems, which unfortunately, we can't really talk about that much in this class, but is a crucial aspect of an operating system for real-time systems. There's a few broad categories of operating system process scheduling algorithms. Call these priority-based or preemptive. Priority-based means that processes are scheduled by the operating system according to priorities. Each process has a priority value, and the operating system generally tries to schedule higher priority processes ahead of lower priority processes. These processes might be assigned statically, meaning they're assigned once and just kept the same value throughout the process lifetime, or they can be dynamic, meaning the priorities change throughout the process. Another broad class of scheduling involves preemption. Does a process just start and run all the way to completion? Or can it be preempted and stopped and put into the block state or put into the ready state and restarted and run a bit at a time as it shares the CPU?